Okay, so today we're on page 2 of notes, and our notes today are about the geometric mean. So we're going to talk with something that you already know about, and that's the word mean. Mean, median, and mode. You probably remember learning that. I know way back in 7th grade in pre-algebra, you probably had it then, if not 8th grade. But to find the arithmetic mean, the math mean of a set of numbers, you add the numbers together, you add the points together, and divide by the number of data points. So, for example, and this is where it might get familiar to you, if you have 5 tests and you're wondering what your average is, at least in the test department, you would add the 5 numbers, and they say 92%, 89%, 85%, 91%, and 89. And I'm going to add all of those together, hopefully on my calc. And I'm going to divide by, let's see, 1, 2, 3, 4, 5. I have 5 test scores. So I'm going to add those all up. And if I did this in a calculator in one swoop, I'd open a parenthesis, add those together, close a parenthesis, divided by 5, and I would get 89.2. So my average in the test department is not an A, it's still a B at 89.2. So that's something from the past. Blast from the past there. Now we're going to talk about the geometric mean. And as most things in geometry, they have something to do with their algebra counterparts or their math counterparts, but we do it a little differently. And the geometric mean is the type of average that finds a value using the product of values. So we solve by multiplying 2 numbers and then taking the square root. So we multiply the 2 numbers and take the square root. So 5 times 15 is what I do first. 5 times 15, and then I take the square root. Now this looks like the proportion of 5 over some number equals some number over 15. 5 times 15 is 75 equals x times x, which is x squared. So if x squared equals 75, well then, hey, x equals the square root of 75. And thank goodness we know how to simplify radicals now, because I'm thinking, okay, what perfect square is a factor of 75 or goes into 75? So if I have 75 cents, it might look like this. I might have 3/4. 3 times 25. 25 is in my perfect square list, and I do know the square root of 25. What number times itself equals 25? That's right, it's 5, so that comes out. That takes care of that 25, but that 3 has to stay in. So my answer, instead of square root of 75, simplified 5√3. So we'll set that up again. The 2 numbers go here and here in our proportion. The x values go in these 2 locations. 5 over x equals x over 15 in this example. So what does this have to do with geometry? Whoops, going a little too far there. This unique proportion appears in a special type of triangle, a right triangle, and it has a lot to do with similarity. So, given any right triangle, as this one is a right triangle, A, B, C, and I know it's a right triangle because that angle at B is 90 degrees, they're showing me that. And if I drop an altitude from the right angle, in this case, that's going to be from B, altitude is perpendicular to the side opposite it. To the side opposite on AC, and let the altitude be called BD. Okay, pretty much looks like this diagram over here. Here's the altitude, BD. Here's my original right triangle, ABC. From the right angle, I dropped a perpendicular line to the hypotenuse. Now there's three triangles. There's an inner triangle, the small one. Here's the small one right here. I'll do that in purple. Okay, that I could call ABD, triangle ABD. Okay, that's the hypotenuse, and here's the long side. I can see that. And then I'm going to change colors here. Then I'm going to look at the inner triangle, which is medium, because the large one is the whole thing. So on this one, I'm going to call it BCD, triangle BCD, because I named it by hypotenuse and long leg. And then the outer large triangle, which is everything we started with, ABC. Let's see, our hypotenuse is here and our long leg is here. So we're going to call it ACB. And that goes hypotenuse, long, short. Okay, this red one, BCD, goes BCD. So here's our red one, B, hypotenuse, long, short. And here's our purple one, ABD, which is little one, hypotenuse, long leg, short leg. What we do know is that these three triangles are similar to each other, which means they have two angles that are the same. We'll be able to prove that. And their sides are proportional. And that's what similar triangles. Remember, we did a whole unit on similar triangles. So, in looking at triangle ABC, the big one, we see that angle ABC is 90. Let me get my, let's see, I did green for the big one. So ABC, we've got this 90-degree angle on our big one. And angle A is O degrees, and angle C is X degrees. Now remember, similar triangles have the same measure of their angles. This means that angle B, I'll just call it angle B, plus angle A plus angle C equals 180 degrees. Okay, because it is a triangle. Now, knowing that the third angle of a triangle must be congruent, that's the third angle theorem. If we have two angles congruent to two angles of another triangle by the third angle theorem, we know the third angles have to be congruent because we have the same leftovers. So let's go to triangle ABD. ABD, that's our purple one. So ABD is our little guy here. We know we have a 90. We know we have the O here because that's what we were given above. That means this part of our right triangle has to be X. Okay? So we have an O, we have a 90. And remember on the big one, we had an O, we had a 90. The third angle was X. So our third angle on the little one, because it's similar, has to be X. On CBD, which is our red one, CBD, we have our 90, we have our X, so we know that this side has to be the O, whatever O is, because we know that these three angles are the same as these three angles, 90, O, and X. 90 and X, therefore the third one is the O degrees. Notice that all three triangles are similar to each other by AA, angle, angle. That was one of our ways that we proved similarity. Here, all we know is the angle measures. They were given to us to start. That's how we know that the little one, the medium one, and the large one are similar. Their angle measures are the same. Okay, it is this unique relationship that creates three different geometric mean relationships. Okay, this is something, let's star it. You really have to focus in here to get this. The altitude. If we're looking for the altitude in a right triangle, that's the line we dropped here, BD. We can go AD over BD equals BD over DC. AD over BD equals BD over DC. So here's our altitude. We don't have the altitude. So AD is the short leg of the little one. So I'm going short of the little. Oh, you know what? I'm going to do that in purple because the little one above I did in purple up here. So I'm going to do AD, the short of the little triangle, is to the long leg of the little triangle, because here's the hypotenuse, is to the long leg as BD, which is going to be our medium size one, and that's in red, so I'll do that one in red. BD represents the short of the medium sized triangle compared to DC, which is the long side opposite the O of the medium. So here's how we can find the altitude, the length of the altitude, BD, if we have enough information. Let's say we have a short leg and we have a long leg. The short from the little one and long from the medium one. We can set up short over long equals short over long, cross, multiply, and divide. Now let's look at number 2. AD, this is when we're looking for AB. Okay, so we're looking for this side over here. And that's the hypotenuse of the little one. Okay, it's the short leg of this big triangle. So I'm going to go AD, so the short of the little triangle is to AB, hypotenuse, as short of the big triangle is to its hypotenuse. So short, I gotta do that in purple, forgetting my colors. Little triangle is purple, short is to hypotenuse as, and I go to AB, that's my big one, so I'm going to green. So AB is the short of the big triangle, the large one, compared to its hypotenuse, which is AC. Now, sometimes we're looking for BC. We have other parts, but maybe we're looking for BC. In that case, we can use CD over BC. So if we have this part, this is the long leg of the medium over its hypotenuse equals the long leg of the large one over its hypotenuse. Okay, so let's see. We're going to use medium first, and medium is red. So medium, CD, right here, long over BC, which is hypotenuse, equals, and BC of the large is green. So we're going to go, the long leg of the large triangle is to its hypotenuse. These break down into two different types of proportions. So first we have the altitude of the large triangle, and then we have the two sides of the large triangle. Okay, study the pictures, take a break here, and study those pictures, and then I want to go on to explain what we call the swing theorems. When we have a triangle, and we're just trying to demonstrate, let's see, I'll draw a triangle here that's a right triangle. And let me just take this and maybe I can get it to turn around. Because I kind of want to show you an altitude drawn. It's not exactly what I wanted, but it'll do. If I draw my altitude, and I'll make it perpendicular, just do black. So I drew my altitude from my 90-degree angle, and an altitude by definition is drawn to the opposite, the hypotenuse side, and it's perpendicular to the hypotenuse side. Now I'm going to use the same letters we used above so it doesn't get too confusing. So my original triangle is ABC. I drew the altitude and I labeled this point D, where the altitude is perpendicularly intersecting, not bisecting, but intersecting with the hypotenuse AC. So in thinking about it, I've got 3 similar triangles. I'm going to label this one the O. Well, maybe we should just give it a measurement. Let me take that off and let's make up some numbers here. Let's take off that O. Let's say, just for example, that it's 40 degrees. And let's say, because I know that the 40, the 90, and the angle at C have to add up to 180, let's say that this one is 50 degrees. Sometimes these things make more sense when you talk about the numbers themselves. It's easier to understand. So in this little, what I might call the little triangle here, I have a 90 degree and I have a 40. So I already have 130. So my leftover angle up here on this triangle on the left, ABD, has to be 50. When I move over to what I might call my medium triangle, I already have a 90 and I have a 50. That adds to 140. So that means this angle over here has to be the 40-degree angle. Okay, because these 3 angles also must add up to 180. So I know by angle, I have 2 angles on this triangle add up to 2 angles on this triangle, and they're the same as the 2 angles on this triangle. So by AA similarity, all 3 triangles are similar. Now we're not saying they're the same size, we're just saying they're similar. Remember, our similarity unit tells us the angles will be the same and the sides will be proportional. So let's say I'm looking for the measure of BD. I want to know what this measure is. Let me change it to colors. Okay, so I want to know what the length of BD is. And let's say I already have another length. Let's say I already have A to D. And since I know A to D, and I'm just making these numbers up, folks, I know that this is, let's say, don't want to make it too hard, 16. And I know D to C is 9. And I want to find the length of the altitude. This is how I can set it up. It's so easy. When I'm looking for the altitude, I need these 2 parts. 16 over x equals x over 9. 16 over x equals x over 9. So I cross multiply and I get x squared equals, let's see, 6 times 9 is 54. So I get 144. Take the square root of both sides. If x squared equals 144, x equals the square root of 144, or 12. Okay, that's when I'm looking for the length of the perpendicular altitude. Now let's say it's one of the other types of problems. Let's say I'm not looking for x at all. Let's say I'm looking for, and I'm trying to come up with some good numbers that are going to work for us. let's say that we have those. Let's say we are looking for, and I'll choose blue. Let's say I have my altitude. Or let's say I'm looking for, let's say I have that length AB, it's 60. I know that this length, making this up, is 36. And I need to know this total length from A to C. This is what I call a swing type problem. This is an altitude problem. And then we're going to have two different types of problems that are swing problems. Let's call this whole line we're looking for, that's the X we're looking for. So hypotenuse is to leg as hypotenuse is to leg. Notice how I'm swinging. I'm going to the left and then I'm coming back. Hypotenuse of the big triangle is to leg of the big triangle as hypotenuse of the little triangle is to its leg. So I want to say the hypotenuse of the big triangle is to its leg as the hypotenuse of the little triangle is to its leg. We call that swinging because we have to go that way. So it's kind of a question of labeling your diagram and seeing, well, why wouldn't I be swinging to the right? You only can swing right or left. Because I don't have any information over here. That's not going to help. All my info's over here. So I know it's a swing to the left. So hypotenuse, leg, hypotenuse, leg. We cross multiply, and 36x equals 3600, 60 times 60. So x would equal 100. This whole length is 100. Okay, we have another type of swing problem, and that's when we're going to the right. These are the non-altitude type problems. These don't involve the altitude. They involve the numbers on the outside, but not BD. Okay, so let's look at some numbers, and let's say we're going the other way. So let's say, trying to get some numbers that are something different. So let's say this time we're looking for, we'll go with purple, we're looking for this leg. And let's say we have these two parts. Let's see, what should I use for these two parts? I can make those up. Let's go 5, and let's make this 8. Okay, can you see by my purple numbers that I've just inserted in here, and I don't need the angles to know any of this, because I've already verified that yes, they would have the same angle measures, so I don't need to know that. All I need to see is that I have a dropped altitude there in a right triangle to know that this will work. So because I need X, I know I'm swinging to the right, not the left. It's not asking for AB, it's asking for BC. So I can look at the large triangle, AC, which is the hypotenuse of the large one, is to this leg, BC, as the hypotenuse of the medium triangle is to this leg, 5. So 8 plus 5 is 13. So A to C is 13 over my leg, which is X, on the large triangle, equals the hypotenuse of the medium triangle over its leg, 5. Now I do want to point out that notice in each of these three proportions I've set up, look what I have. A number over x equals x over a number. X over a number equals a number over x. Okay, I'm looking to make sure that I have something I can work out. X times x I know is x squared. 13 times 5 is 65. So if x squared equals 65, x equals the square root of 65. Let's see, what numbers go into 65? It's not one of my perfect squares. I know 5 goes into there, but 10 does not. So I'm just thinking, can I simplify this? Let's see, how many times does 5 go in there? 13 times 5. What factors do 13 and 5 have? Well, 13 only has 13 and 1. 5 only has 5 and 1. You know what? This is one of those radicals that can't be simplified because there are no perfect squares in 13 or 5. So there's really nothing I can do, and here's my answer. The square root of 65, exact answer, not rounded. 8 point something, I don't want to see. Okay, hopefully this gives you a good indication. It's going to help you do your worksheet on 8 and 9. You will either be looking for altitude problems or one of the two swing problems and work on pages 8 and 9. It worked. This works okay. My computer is messed up. Okay, so you can look at my notes too for tomorrow to see if you like them.
Yeah,
Or see if it makes sense to you, because Laura and I do that swing thing. You either have an altitude problem or you have a swing problem. It all boils down to that.
Right.
So you know you have a swing problem if it doesn't involve the altitude. Okay, if there's no x there, no number, you're probably going this way or you're going this way. It just depends on where the numbers and where the variables are.
Right.
Oh, if there's nothing on this side, you're swinging that way. If there's nothing over here, you're swinging that way. So I went on after this and went through the swing method and the altitude method, how that's what they're looking for. But even so, there's
You
some
doing that
problems in the
tomorrow?
homework. Yeah.
My kids needed more on the radicals.
Mine might have, but they just did the video and then did their homework.
Yeah. I mean, I did
I'm just going to
6 examples, different, but just based on the questions, you know. they
Did you
needed-
do all those problems in the notes?
No, we only did 6.
Oh, I did all of page
Why not?
1.
Yeah, I cut down to 6 of those,
Yeah.
so. should've
Well,
done
it was a
more.
15-minute video, and this one is going to be at least 15. I never know where my video goes.
I'll look at yours and look at that swing method.
Yeah.
I don't know the swing method, so I'm gonna have to.
I know,
see it.
and I don't know. I think I learned that at Shawnee Mission East, and when I told
But
it
I'm
to
gonna-
Laura, it made sense to her, and now she uses it.
Yeah, I've gotta look at some with. I gotta look at some of the numbers. Because it just,
Well, some of these problems are kind of hard. Okay, if you're doing the same 8 and 9, those problems on the back on page 9 are difficult because they're asking for X, Y, and Z. Holy smokes, the answers are like horrible fractions too.
fractions or radicals?
Well, they're fractions, and then it says up here round to 2 decimal places. Right there. This is an old thing though. You may not be doing that one on page 9.
No, I kept those.
Oh,
I
and then I saw that it said rounded 2 decimals, so then I went on and
I
did
think I
that.
kept those.
I think that's way too ugly for them learning the concept. But whatever.
But I want them to keep it as a,
It says rounded 2 decimals.
right, but I'd take a.
I never want them rounding to 2 decimals from
No,
here on.
I would, yeah, no, I want them to leave it as fractions if they can.
Yeah. But I thought that was kind of ugly when you're subtracting like an ugly amount
Yeah.
from and to get the rest of it and all that. Okay, I'm gonna save this and then I'll send you the copy,
Okay.
okay?
No.